Okay, now we're going to talk about descriptive statistics. Some of the topics we're going to cover today are proportions and percentages, frequency distributions, and ratios and rates. First, let's look at a statistical data set. So maybe in the past you've seen a data set before. Data sets often come in the form of an Excel spreadsheet or Google Sheets spreadsheet, but they look like this, where you have rows for each case, and you have a name at the top of each column, and each column represents a variable. And you'll see you have on the left-hand side, it looks like state. We have county as another variable, total pot, which is probably the total population in that county, percent unep, which is percent unemployed, percent homeowners, percent college, so on and so forth. So each column represents a variable, and each row represents a case or observation, whatever our unit of analysis is. So if we were to look at this, we'd say that our unit of analysis is the county level within each state. See some Arkansas listed on the left. We also see California, so it's a county within a state. So descriptive statistics, it's a branch of stats that allows us to describe or summarize what's going on with the variables in our data set. Doing so allows us to create manageable summaries about our data in order to quickly and easily understand what's going on. Right? What are the most important characteristics in our data set? Our descriptive statistics often refer to a variety of things, but mainly they are measures of central tendency. What is average or typical of the distribution? Measures of variability or dispersion. And then we have things like percentages, proportions, rates and ratios, and frequency distributions. So measures of central tendency. Measures of central tendency are those that describe, so descriptive statistics, they describe what's average or what's typical of a variable in our data set. So some of our common ones are the mean, median, and mode. So the mean is just the variable's average, right? The distribution of that variable's average. So it's calculated by adding up all the values for each case and then dividing up by the total number of cases. The median is the middlemost point of all those values. So you order them in consecutively, and you find the middlemost value. So maybe you've heard of things like mean age or average age, but things that are a little bit more extreme, you might use the median for, right? So you might have heard of median household income or median property value, right? And there are reasons for that, and I'll explain that later. And then finally, the mode, the most commonly occurring value, right? So mean, median, mode, you may have heard of these before in like an intro algebra class. These are measures of central tendency. They describe what's going on towards the middle or most commonly in our distribution for a variable. Measures of variability or dispersion are range and standard deviation. Range is just, you've heard this before, it's just the spread of values and calculated by subtracting the maximum value on that variable from the minimum value on that variable. And then the standard deviation is the average deviation from the mean. So standard deviation is important because for each variable, you're going to calculate a mean, but you don't know if most people are clustered close to that mean or far away from that mean. The standard deviation allows us to determine, on average, how much are people away from that mean. It's the average distance from the average. You can think of it that way. Portions and percentages. These are ways that we can standardize our various values from our data. So percentages standardized to a denominator of 100. You've heard that things are out of 100%. And then proportions standardized to a denominator of 1. They allow us to compare groups of different sizes, and you can use these calculations for categorical and continuous variables. So ordinal, nominal, interval, and ratio variables. So percentage is the number of cases over n times 100. Proportion is the number of cases over n. Right? So here's an example. Of the 269 cases handled by the court, 167 resulted in prison sentences of 5 years or more. So a proportion would be 167 over 269. And then a percentage is just that same calculation times 100. So if we're trying to standardize to 100. So 0.62 for proportion, which turns into 62.08%. Frequency distribution is a table, and often you can use a graph in addition to a table. And it displays the number of cases within each category of a variable. So let's think of our race variable. We can have a bunch of different observations, units, individuals in our sample, and we ask them their race or ethnicity. You know, this many said white, this many said black, this many said Latino, this many said Asian, this many said native, this many said other, right? And it would just tell us how many fall in each of those racial categories. Now, with the frequency distribution, as I just said, this can be displayed in bar charts as counts or in pie charts as percentages, right? So you can convert the number of people in each category into percentages, and then you can use a pie chart. But oftentimes, we typically display these kinds of variables as a bar chart. So here is an example. We have N of 1460 people who were surveyed. So that should be a small N, not a big N, because that is a sample. They were surveyed about their marital status. Marital status is a nominal variable since you can't rank order the values. So we have married, widowed, divorced, separated, and never married. Those can't be rank ordered. You might think, well, never married comes before married, and then divorced comes after married. But some people might get widowed and not divorced. Some people might get separated and then divorced. Some people might be separated and then widowed, right? So because you can fall into various categories at various times in one's life, you can't rank order them. So we treat it as a nominal variable. Here in the middle, we see the frequency table. So the frequency distribution table has each category. So married is one category, widowed is another category under the variable marital status. We see frequency, so it's the number of people in our data set who identified as married. 661 identified as married. 138 identified as widowed, so on and so forth, for a total of 1460. Then we can calculate percentages, right? So 661 are married out of 1460 should be 45.27%. So we can use this information and create a bar chart of marital status. So a bar representing 661, another bar representing 138, another bar representing divorced, 239. Or we can use a pie chart and say 45% of this sample is married, 9.45% is widowed, so on and so forth. Here's just a snippet of the data set, what it looks like. So each row representing a person, and it's their ID number and their marital status. Here we see the breakdown of the pie chart. So instead of using counts, all we did was use the percentages out of a total. Now, if we remember, a pie is how much percent? That's right, it's 100%. So we're looking for each slice to represent its relevant percentage out of 100. Right? So all of these should sum to 100, and the size of each slice in that pie should represent the slice of that percentage value. Here's another one. So it's a frequency table depicting support for gun control. This is an ordinal variable because you can rank order the categories, and we ask them, what is your level of support for gun control? Low support, medium support, or high support? People were asked to categorize themselves along this kind of scale. 156 said low, 123 said medium, 95 said high. This is out of 374 people. So much like we did with the last one, we can calculate percentages for each category of gun control. So low is 41.71%, medium 32.89, high 25.40 of 100%. And we can use these percentages again to line up in a pie chart. So medium is 32.89, high is 25.4, low is 41.71. And the size of these pies represent their relative irrelevant percentages. So when we're reporting percentages, we always want to report the number of observations along with the percentages. So what we want to be careful of is anytime we're reporting uh, a table or a chart like that, and it doesn't have the actual number of cases, right? Because with a small number of cases, percentages uh, can change drastically with minor changes in the data. So let's say instead of 374 people, we had 3 people, right? And let's say 2 of them said uh, moderate or medium support, and 1 said low support. Because of that, the bar chart's going to look wildly different, right? This is one of these notes is important, or this note is important because we also want to think about our sample, right? Ultimately, like I said in previous slides, ultimately what we want to do is infer or generalize to a population. If we have too few cases, that's a small, even smaller subset of the population. So how do we generalize to a population when we only have such a small number of cases, right? How do we ensure that our small sample is representative? Chances are it's not. And so we always want to make sure that we're working in the realm of larger samples because we want to explain more of what's going on in the population. That said, it's always important to make sure you're highlighting the number of cases in your charts, right? Whether that's percentages and the number of cases, so small n number of cases, or in a bar chart listing the small n number of cases, but also the number of cases or the frequency within each category. So this bar is, 70 people, this other bar is 25 people, so on and so forth. All right, ratios. Ratios are a comparison of 2 numbers or a comparison of numbers for 2 categories. Um, and they tell us how much one category outnumbers the other, right? So we oftentimes compare uh, two values together, right? So let's say we're comparing the number of students on campus to the number of faculty on campus. So a few years ago, we had, let's say, in one major, we had 4,300 students or 4,304 students, and the number of faculty was 269. A student to faculty ratio would be the number of the first category, so students, divided by the number of the second category, so faculty. So student to faculty would be 4,304 divided by 269. And that value is 16. For a ratio, we can explain it like odds, like we do, like, oh, you have a 4-to-1 chance to win, or, a 2-to-1 chance to win. Right? Ratio can be explained here as 16-to-1. So that means there are 16 students for every 1 faculty member. Right? 16-to-1. We can do the same thing for a number of Protestant families as a ratio compared to number of Catholic families. The ratio of Protestants to Catholics would be 1370 divided by 930, which is 1.47. So this would mean there are 1.47 Protestant families for every Catholic family, right? Or a 1.47-to-1. Another way of putting it. Rates. are similar to ratios. So rates and ratios are very similar. However, with rates, you're comparing two quantities that have different kinds of units. With ratios, we were comparing people, right? Students to faculty, uh, Protestants to Catholics. Those are people compared to people. With rates, it's one measure compared to something else that is in a different measure, right? So, for example, we can calculate crime rate per capita, which is crime rate or the number of crimes per person in a population. So, crime rate per capita would be the number of crimes in an area divided by the total population in an area. So, one, we're comparing numbers of crimes to people, right? Crimes to people, right? So that's how rates and ratios differ. Rates are two different units. We can also do something for birth rate per capita, which is the number of births divided by the total number of people in the population, right? So the births per person in the population. Um, I put this here as a note. You can also calculate it differently. So instead of doing per capita, we can say per 100,000 people, which means how many births or how many crimes per 100,000 people in that area. But to do this, you have to do an extra division step. So you first divide the total population by 100,000 and then divide crimes by that new calculation. So crime rate per 100,000 would be number of crimes divided by total population divided by 100,000.